Okay, tonight we are going to do a bit more basics educational stuff. So it's a bit weird because there's thousands of videos on about what we're about to talk about on the internet, if that makes sense. But I just feel like I need to be complete in this channel. So anyway, we're going to talk about resistors. Are these the ones that I want? Hold on. No. These are the ones that I want. Okay, so we're going to be talking about these things again, resistors, but not really about resistors. What we're really going to be talking about is part one, I think, part one of a two-part series about parallel and serial circuits and the difference between the two things. So what I basically mean, so this is an example, to start off, of a serial circuit. So this actually could be any electronic component that has two little legs. So the things that I've done so far are LEDs and resistors, but also buttons, I guess. No, not buttons, but diodes, which we'll get on to soon. So it could be one of these guys. It could be like a little LED. Or it could be things we haven't looked at yet, like capacitors and inductors. But we're going to talk about things that just have resistance at the moment. So they don't have to technically be resistors. Like they could be like a speaker or something. But for now we'll just talk about resistors. So just to remind you, this is a resistor. And if we put a resistor so that one resistor is linked to another resistor like this, so they go, so either the electric current, you can imagine, flows in this way through here, or it flows in that way through there. It's not that important here. All that matters is that they go from one to the other one, and that's a serial circuit, or a serial. The components are laid out in a serial fashion, we'll say. So I'm sure there's a correct term for this, and I'm completely forgetting it. It's just it's serial. That's the important thing. So if you see the word serial, it means that they're laid out like this. But if the components can be laid out another way, or we can look at it another way, and that way, I'll bring that one back, is, well actually, we'll just quickly go back. No, we'll come back to this one here. So this is 100 ohm. So go look up the videos I did about resistance to do a little more to know what that means. But that's 100 ohms and that's 200 ohms, and I talked about this in those videos. So if you go back to those videos, you'll remember that the total resistance across here is this resistance plus this resistance. So this is 100, this is 200, then the total resistance is 300, which makes sense. If you're going to have to struggle through this thing and you're going to have to struggle through this thing, then the total struggling you're going to have to do is the total of going through both of those. One way of thinking about it. The other way though, the other way of laying out components is in parallel. So they come in here and they're like, this is the where the current is coming in through, or it could be going out, it doesn't matter. It's coming in this way, we'll say, and then it splits off into two, goes into two separate items, and then comes back down into here and goes out the other side. So this is called a parallel arrangement, so a parallel circuit. I don't like saying the word circuit because we haven't got the rest of the bits and pieces in here. But the parallel arrangement of components. So here in this case, you've still got a 100 ohm and a 200 ohm, but to work out what the resistance is between this point here and this point here is slightly more complicated. And this is because when you come in here, if you imagine you're a little bit of electric current coming in here, you have two possible ways of going. And so if you imagine it's a whole bunch of little tiny circles, little electrons, this is not really exactly what might be happening at the physical level. But if you imagine that there's little electrons coming in here, then they have two choices, and so some of them will go this way and some of them will go this way. And to cut to the chase and to give away a bit at the end, they're going to split up roughly so that 2/3 of them are going to go this way, and then the other ones are going to go that way. So this is a slightly harder way of going. It was twice as hard to go this way, but it's still possible to go this way, and it's half. It's easier to go this way. So most of them are going to go this way, and some of them are going to go this way. And we'll talk a little bit about why they go both paths and why they split up like that in a second. But first we're going to come back. So we're going to split this up. We're going to do some playing around with the circuit board. if I haven't lost my multimeter. And we don't actually have to power things up just yet, but we will. So I'll bring that in just in case. But here we go. Here's a very complicated thing with mathematics on it. And so this is meant to be a general thing. So in here I have 3 resistance things. R1, R2, R3. But you could have, you know, as many R things as you want. And so this is the total resistance, which is RT. So this is just basically phrasing what I said before. RT is R1 plus R2 plus R3. Sorry, when I did this, I swapped around between doing what's it called? Suffix something. I've completely forgotten the word, but I'm putting it down the bottom and putting it right next to it, which is the way I'd normally do it, like this way. A subscript way, sorry. So excuse me for swapping in around between the two. Just ignore that, or go with it. And so here, this is the interesting bit here, and that the current. So this is actually, I didn't write this down, but this is Kirchhoff's current laws, I think it is what it's called, that we're looking at. No, it's not. They ignore what I just said. That's the next bit here. But anyway, the point here is that the current flowing through all of these things is the same through each resistor, and that makes sense, right? So you don't remember what I said a long time ago in my resistor rambles, is that the current doesn't bunch up in little bits, and it doesn't like sort of bunch up here. So you can't have more current going through here and then less current going through here, because then some of that current would start to sort of pile up at this region here, because they can't, you know, they're waiting to go through this bit here. So if 10 went through here but only 5 went through there, then you've got 5 sitting around doing nothing. And then you've got another 10 coming along, as you know, because it's continually flowing along, piling up, and so it just gets worse and worse and worse. So what happens is that the current is the same all the way through in a series circuit. And this is the voltage, this is the total voltage drop. So the voltage drop between here and here. So how much voltage do we spend to get from here to here is going to be the voltage that we spend to get past this bit, plus the voltage we spent to get past this bit, plus the voltage we spent to get past this bit. So that's the total drop in voltage from this point to there. Or if you're looking at the other way around, from here to there, depending on how your circuit is set up. Okay, and it doesn't, in most cases, it doesn't, the thing is really important in the series things, it doesn't matter which way around these things usually go for most components. Well, for all the ones that I'm going to be talking about anyhow, that if this resistor was over here and that one was over here, it would still be exactly the same kind of effect in the end. It does matter, of course, if things split off from that point there, then you can't swap those two around and get the same result. But if they're all like here and there's no branching off or anything like this, then it doesn't matter which way around these things go. And this happens if you have an LED here. If the LED was here and the resistor was here, it's the same as if the LED was there and then the resistor was here. So I hope that kind of makes sense. And the next page we've got is the complicated stuff. So we're mainly trying to introduce the idea of parallel circuits. And I was going to go through the maths of where this comes from. But since I'm never going to finish these videos if I do everything, I'll just do this one now and we'll come back to where this came from. But here we go. We have 3 resistors and they're split up into a parallel circuit. So they're going through here, so they come in here and they go through here, and this is the interesting thing. So this is the opposite way around. We'll ignore how we calculate the total resistance for now, but the voltage drop across each of these has to be the same, which is the interesting thing. So we're basically having to drop the same amount of voltage. So we're here, and so the voltage drop is the same across R3, across R2, and across R1 between these 2 points. And I could just say, that's just the way it is. But I guess what's the best way of explaining it? Well, you have to spend, you've got to, yeah, we'll just say for now, hopefully I'll come up with a good way of explaining why that is in a second. But what happens is the current splits up in this case here. So the total current that goes through these three is the current that's going through this one, and then the current going through this one, and then the current going through that one, which makes sense. So if you've got a bunch of little electrons and you want to get them from this side to here, well, the number that you get from this side over to here is going to be the number that you get going through here plus the number that you get going through here plus the number that you get going through here, if that sort of makes sense. And the voltage drops have to be the same because I'm trying to say, because if it wasn't the same, then you could have dropped it a bit more and got a bit more electrons through to the other side. But it's too late at night for me to think of a really clever way of explaining why that is true. It just is. So if you're forcing the force you use to get all the current through here. Alright, if you didn't use as much force through one of these ones, then you probably could have got a bit more. You could have got a bit more current if you had used more force. That doesn't make any sense. We'll come back to why this is true. There's got to be an easy way. But the consequence of this sort of flipping things around is, actually, if you look at it that way, there's an easy way of getting why this comes out. Why the resistances are hard to calculate when they're in parallel. It's because you've flipped everything around, and if you do the algebra you'll see. But the point here, because in the previous one, this is very rambly, in the previous one the current remained the same across all the resistors, but the voltage was divided up. And in this case here, the voltage is the same across all these things, but the current is divided up. And so the resistance basically looks like the flipped side of the series equation. The series is you just add up the resistances, which seems nice. But here you have this very odd way of calculating things, which is the resistance, the total resist, 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus blah 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 to 1 over Rn, or 1 over R3 in this case here. So I wrote that over here. So 1 over RT is that and that and that, and you can't just say, well, that's the same thing as that just turned over. So if you know your maths, that's the reciprocal of RT. But this will come about by looking at these facts here. And I was going to do things. We'll do a video later on about the algebra of this and how we come up with this equation here, because it looks like it comes out of the blue. It's like, how do you get this kind of strange thing? But let's actually do. Hold on. We're gonna do an example first. No, let's just finish it off. I'm gonna like do some practical stuff. That's what they do at school, right? They do practical bits, and then they do the theory. But we're just gonna keep going through. The important thing about the resistances, I think, is you don't really, if you're going to just do it for playing, if you're doing electronics to play around with, you don't need to know the maths that much. Like, you don't have to be doing this algebra all the time. But what you want to get is some sort of intuitive feel for what happens here. And I think the important thing is, well, you can actually do, there's a simplified way of doing it if there's only 2 resistors in parallel. And the neat thing about if there's only 2 resistors in parallel is, well, that's basically, that covers all the cases of resistors in parallel, because you can start off, work out what the total resistance of this thing is by ignoring this one, and that gives you like a resistance for just these 2 going across here, and then you end up with 2 more. So you end up with that one, and then you've got this one, and then you end up now with again 2 resistances. So you can then calculate that to get your final RT, which is the result over here, so in pen. So we're going to go through the simple way with 2. So here I've written 1 equals RT equals 1 over R1 plus 1 over R2. And so all I did then was I multiplied, I added an R2 to the top and R2 to the bottom, and R2 divided by R2 is 1. So that's this term is the same as that term. So just going through the algebra here. Plus, and I did the same trick here, so I put an R1 over R1, which is 1, So this is the same as this term. So 1 over R2 is the same as R1 over R1 times R2. So you could say, if you don't know the algebra for this, it's like if I said 3 over 3 times R, then the 3's will cancel out, and it will still be 1 over R2. So now we've got this equation, and now the bottom bits, the denominators, are the same. So then we can link the two together, and then we've got R2 plus R1 equals over R1 times R2 equals 1 over RT. And if you flip that over, get the reciprocal, you end up with R total equals R1 times R2 over R2 plus R1. Well, swap them around so it makes sense. And then we're going over here, and the important thing, so again, don't worry about this if you don't like maths. So I think if you're going to do this, you kind of have to like maths a little bit. And I'm sorry if this is not a very good explanation, but there are thousands on the internet, and there's thousands in books. This is like standard stuff in every book. So just go look it up. I just feel like I have to explain it, even if I do a terrible job. And the last thing, though, is what happens if R1 and R2 are the same. So we just call them R. And in which case, so R1 and R2 are the same, or they are, so then RT will equal R squared over 2R. And so we can chop off one of the R's, we can cancel out one of the R's, and then we end up with R over 2. And that just means if we put two resistors in parallel, we get half the resistance, which makes a lot of sense, right? So if you have two if you give electric current, we're gonna use these, so I'm gonna take them off anyhow. If you give electric current two options, so they can go down this path or that path, well then you're going to be able to get twice as many through. So the same number that you get before would go through this side, and the same number you get before would go through this side, so you end up with twice as many going through. So that means you, if you're getting twice as many going through, then you're getting half the resistance. Is probably, I hope that makes sense. But it should be kind of intuitive, right? Like, it's easier if there's two paths and they're the same to get through than there is if there's only one path, or if they're different things. Well, that's not true. But the really important thing here that I didn't show is that the total resistance in a parallel circuit will always be less than the least resistance of any of the particular paths. Because say this is the smallest path, the top one, well then you're always going to get what you had before. Say you didn't have the bottom one, then you're always going to get as much current going through that path, but you've also got another path, so you're going to get a little bit more, at least a little bit more current going through the other way. So you're always going to get more current going through, and if you get more current going through, then the resistance is lower. That's what it means, basically, to say the resistance is lower, that you're getting more current through for the same voltage. And now we just have one last thing. So that's one intuitive thing, is that if the resistances are the same, you don't have to care about the math. You've just halved the total resistance going through. So if you have, I'll keep losing these things, don't I? If you have, in this case here, this is a 10,000K, a 10,000 ohm resistor, and I wanted a 5,000 ohm resistor. Well, if I put two of them in parallel, I've got a 5,000 ohm resistor. And in fact, if you keep adding them on, then you'll get them divided by 3. So if I do this, if I have 3 of them, then it's actually going to be 10,000 divided by 3. So the total resistance will be 3,300. And so on. So if I had 4, it would be 2,500, and so on, and so on, and so on. And the other important thing is, what would happen if R1 is much bigger than R2? So in this case here, what happens if you have two paths and one resistance is way higher, much higher than the other resistance? What's the effective result? Well, in this case here, so going back here, this is what I just wrote before. RT equals R1 over R2 times, R1 times R2 over, I really should have put it the other way around, R1 plus R2. But if R1 is is much bigger. What have I got? R1 is much bigger. So if R1 is much bigger than R2, and if you're looking at the denominator, then R2 doesn't really matter much, and so it's approximately the same as R1 times R2 over R1. It's kind of like limit theory if you've done that kind of stuff. Like as this one gets much bigger, then the impact of this is much less. So if I had what's a good thing? Say, I don't know. I'll try and come up with values in a second. So it's this means approximately. So this is approximately. I think that's what the symbol for approximately is. Approximately R1 over R1. Right, R1 times R2 over R1, which is approximately, because these two cancel out in that case, equal to R2. So if R1 is much bigger than R2, then the total resistance is pretty close to being R2. So that makes perfect sense, right? If you think about it, just looking at this little picture here, if one of these is huge and is really hard to get through, then most of the current's just going to go through the other one. And that's all that's saying. And I think that's the most important thing to get out of all that. So the next one is going to be more interesting, is what happens if you put things like diodes in there, or particular LEDs that hold on, that don't act in the same way as a resistor. So a resistor is sort of like a linear device. As the voltage changes across it, or as the current changes, whichever is happening at the time, the other one reacts in a linear way. So the resistance is just tying voltage and current together in a sort of set relationship. So if the voltage increases by 10, then the current will increase by whatever, by a similar amount. That's not making too much sense, but we'll talk about that next time. That's not for today, it's for next time. But this is a multimeter, so we'll just do some multimeter fun. So here, this is a good way of putting two resistors in parallel on a breadboard. So the little pins, I'm going to bring this up close, put in the same line. So in this case they're here in line 12, and in this one here they're in line 20, and so they are now in parallel because everything here is connected. And so bring back my little diagram, everything here is connected, and so these are 10,000 ohm. So here's my little thing, it should be set to resist. So this is a different multimeter, I couldn't find the one from last time, which is a shame because that's the one that I wanted to use, and just checking it's not right behind the thing. So if I take one of these things and I hold it like this, does this have a little light? Apparently the light doesn't work. I hope that it is visible. Right, if I put this on here, it will say 9.93. In this case here, it's actually also using me. So it's actually a parallel circuit when you hold it like this, because it's also going through my body. So if I take my finger off it, it actually goes up. The resistance goes up slightly, because in this case here, you're making a parallel circuit with me as the other resistor. So it's actually going through my body and coming out the other side. And that makes a difference that you can see on the display. So it's gone down a little bit. So if I take my finger off, it goes back up. So in that case, this is a 10,000 ohm resistor. So it's not going to be the same as what I did here. So I'm not using those numbers. So we should have done some practice with this one. Well, in this case here, we'll just quickly do it. So 1 over RT is 1 over 100 plus 1 over 200. So 1 over 100 is 2 over 200. So 2 over 200 plus 1 over 200 is 3 over 200. So the total, so 1 over RT is equal to 3 over 200, which is equal, so RT will be 200 divided by 3, which will be 200 divided by 3, should be about 66, right? So 66-ish ohms. which kind of makes sense. So it's always going to be less than the smallest one, which is 100 ohms. And so anyway, that's how it works out. I think I should have done that actually. I had gone through and worked that out and talked about it. So here we'll do this. So hopefully on here, I should just pick one of these. Hopefully, if they are actually connected up, it will say, it still says they're 10K. Well, that's rotten. I feel like if one of them is not plugged in properly, then it's going to say, what have I done? All right. Okay, well, I'm just gonna, we'll try. Maybe there's something wrong with the breadboard. Well, we'll just tie them together and see what happens. Alright, and we'll do the holding out my hand thing. What? Well, that's interesting. Really? This is basically, I'm actually surprised at this. Why does this not work? What have I done wrong? Let's just test each of these. So we're going to work this out. How much time have we got left? 2 minutes and 40 seconds. Really? That took that long to say? Oh, well, look at that. Okay, so I picked up the wrong box. Really? Really? These were all 10K. Okay. So actually that did work. So I thought they were both 10K, and so I'm a bit perplexed as to why it says that it's still 10K with two of them, but in fact they are 20K. And so when I put them in parallel, they come out at 10K, which is funny when you think about it. So let's do this again, and we'll test the resistance. I wanted to actually do the testing the voltage bit as well. So there we go. It says, I don't know if it's very, but it actually says 5000K there. So it did work. It does work when they put them in parallel. If you take one of them out, it will take 10,000K. Alright, and we better quickly, we've got just enough time. If you put them in series, like that. So in this case here, what's that mark for? One of these legs is connected to the other leg there through this line. And so now, what are we going to believe it's going to be? Well, they're in series, so we add the resistances together. It's 10,000 plus 10,000, so it should say 20,000K if everything goes. And it's kind of going to work. It does after a while. Hold on. 20,000K exactly on the dollar. So that was pretty good. So a shame we didn't go into the voltages and the voltage drops, but we're going to do that. We'll do that for the next video when we talk about LEDs and everything else. And that was actually supposed to be a 15-minute video. So, alright. Sorry for the rambles. Thanks for watching. Catch you next time. Bye.